Dear colleagues, welcome. We would like to present our work, Percolation Models of Competitions and Monopoly. The authors of the work are Doctor of Technical Sciences, Professor Ivan Grabar, Head of the Departments of Police at National University, Olena Kilnitska and Maryna Yaremova, Associate Professors of Police at National University, and Yuri Kubrak, Associate Professor of Zhytomyr Polytechnic State University, Ukraine. A brief review of recent publications shows that the phenomenon of competitions is inherent not only in market economies but also in political parties, as well as processing in ecology, biology, the physics of critical phenomena, sports competitions, and other domains. These research studies demonstrate that political party competitions requires thorough scientific investigation. It confirms that competitions among political parties for public support is an important criterion for the democratization of the political processes and a key factor in legitimizing state power by increasing citizens' political activity during election period and involving them in active political engagement. The nature of political party competitions depends on the type of political regime and the level of political culture of citizens. In democratic political regimes, political parties operate under equal conditions. To a significant extent, political competitions among parties takes place through informal channels, where official legal norms often serves only as formal confirmation of previously achieved informal agreements between the governments and the oppositions. Researchers show that competitions and monopoly as two sides of single phenomenon characteristic of synergetic systems of interacting elements competing for the distribution of a certain resource inevitably lead the system to a certain cumulative rating frequency distribution as an interacting set, that is, to an attractor. As will be shown further, the closer the systems is to the states of free or perfect competitions, the more accurately it is described by a semi-logarithmic models with a higher correlation coefficient. Conversely, the closer the systems approaches the phase transition point, for example monopoly, the greater the correlation coefficient obtained for the hyperbolic model. In previous works, we have provided important generalizations of the theory and practice of applying percolation models, as well as derive several essential engineering formulas for the quantitatively estimating the percolation threshold in domains with different fractal dimensions. They also propose a solution to problems regarding the ratio of the winner's results in a competitive contest to the total achievements of all participants, demonstrating that under conditions of perfect competitions, a correct general solution to this problem exists. Percolation model enable quantitative forecasting with repeated reproductions of the results of the kinetics of competing processes in many types of competitions in biology, ecology, psychology, economics, politics, sports, etc. At the same time, there is an uneven distribution of participants in the process according to the same generalization criterion QI: financial achievements, real estate, agricultural and forest land, points, goals, seconds in sport competitions, etc. As it turns out, dependence QI from I form rating frequency diagrams, which in all the above cases, then competition is close to perfect, are described by semi-logarithmic dependencies with a very high correlation coefficient. For quantitative modeling of phase transitions, we have developed the following unique software products. First one is Percol. These products set a statistical simulation based on the specified control parameter PA in the area G with dimensions AX, AY, and AZ, where A is the range from 0 to 500. Displays the area G and the clusters formed on it. Automatically colors the clusters in black and white or color mode. Determines the presence or absence of the connection cluster from the left to the right boundary of the area G, fills in the test report. And second one, Percol statistics. Extend the Percol software with statistical processing of cluster sizes, including their logging and ranking by size. Allows the rating frequency diagrams constructions for any statistical simulations on region G. In general, all dependencies of the rating frequency diagrams of percolation clusters, at least for probability of filling from 0.6 to 0.62, are described by differential equation 1. For m equal -1, in the case of perfect competitions, this gives equation 2. For m less than -1, integration 1 allows us to obtain hyperbolic dependencies that are typical for modeling rating frequency diagram in the area of imperfect competitions and monopoly, see equation 3. The obtaining dependencies 2 and 3 confirms their applicability to all types of competitions where there is an uneven distribution of participants in the processes according to the same generalization criterion Q. The generalized parameter Q can be financial achievements, real estates, agricultural and forest lands, points, goals, seconds in sport competitions, cluster sizes in classical percolation, etc. Let us consider the two-component percolation model. Let two components, A and B, mix in a certain region omega with fractal dimension D. D can take both integer and fractional values. Let us divide the region omega into n cells. Let each cells n occupy component A with probability p and component B with probability 1 minus p. Then we obtain the dependency 4. Let us denote the characteristic size of the region omega by parameter L. Then we obtain the relationship 5, where D is the fractal dimension of space. When the control parameter changes, the probability P of filling the region G with components A is in the range from 0 to the percolation threshold P star. The probability of connection cluster appearing of the region omega can be found using the equations 7 and 8. From the point of view of competitive process theory, this means the formations of the connection clusters or the monopolization of the part of the entire region omega. We have shown that the percolation threshold depends primarily on the fractal dimensions of the region omega, strong dependence, and weakly depends on L and the method of dividing the region omega into cells. As we have shown in previous works, in the case of Cartesian divisions of the region omega, the percolation threshold is very well described by Professor Grabar's Cartesian approximations, see relation 9. Table 1, 2, and 3 show the results of modeling cluster formation for control parameters value p ranging from 0.50 to 0.62. We remind that for a two-dimensional model, according to Professor Grabar Cartesian approximation, we have a percolation threshold p star equal 0.5945. The obtained rating frequency diagrams are best approximated with the highest correlation coefficient in semi-logarithmic coordinates. For perfect competitions by dependence 2, slide 4, and for imperfect competitions and monopoly by dependence 3 on slide 4, with values k ranging from 0.5 to 1.5. Figure 1 on next slide 8, 9, and 10 will show images of percolation clusters obtained in a wide range of values of the control parameter P on a two-dimensional square area of 250 by 250. From figure 1, it follows that the sizes of cluster increase significantly with an increase of the control parameter P, and at P ranging from 0.59 to 0.62 reach the monopoly region. For example, one of the several large clusters capture practically the entire region omega equal 250 by 250. Table 2 on previous slide show that in this case the winner share of the total achievements of all n participants exceeds 0.5. At the same time, the share of winner of competitive contest under conditions of perfect competitions can be obtained automatically, analytically for any number of participants in competitive contest and see equation 10. As can be seen from table 2 on slide 6, the winner's share in perfect competitions for n equals 25 does not exceed 14.3%. On next slides, you can see these results of modeling cluster formation. Here you can see that increasing of probability of filling the area increases the probability of connection cluster appearing. Figure 2 shows the rate and frequency diagrams charts for each of the 4 areas of percolation modeling of cluster formation that met the criteria of perfect competition, imperfect competitions, and monopoly. Figure 3 shows that the asymmetry parameter phi correlates closely with the values of the control parameter p. Figures 4 and 5 show that the parameter of the rate and frequency diagram dependencies for perfect competitions, imperfect competitions, and monopoly are auto-modeled. For example, their independence between their parameters. In figure 6, parameter k, independence free, on slide 4, correlates well with the value of control parameter p. And our conclusions. For quantitative modeling of geometric fast transitions in percolation problems, the authors have developed original software products called Percol and Percol Statistics. Numerical modeling of cluster formation was performed dependent on the approximation to the percolation threshold P star, and a statistical evaluation of each of the formed clusters was performed. For each of modeling options, rating frequency diagrams of cluster sizes were obtained. Their best approximation in semi-logarithmic coordinates was shown. This satisfies the differential equation 1. It was confirmed that the percolation threshold P star, according to the Professor Grabar Cartesian approximation, depends only on the fractal dimension d of region omega, see equation 2. Experimental and theoretical estimates of the proportion of winners in competitive contest have been obtained for conditions of perfect and imperfect competition as well as for conditions of monopoly. Thank you very much for your attention. If you have any questions, please write to emails addresses indicated below on this slide. Thank you.